with a single layer perceptron. The difference between a single layer perceptron and a multi-layer perceptron or a multi-layer neural network is that a single layer perceptron can only differentiate in a linearly separable data. It can only differentiate linearly separable data. So the primary difference is that, and what multi-layer perceptron achieves is that by adding additional layers, one can have a what is it called? A nonlinear activation function at each layer here. Assume another layer of neurons are here. At each layer, there's a nonlinear activation that allows the network to learn nonlinear functions. So the primary difference is that, but the main idea stays the same for a multi-layer perceptron or a single-layer perceptron in terms of its learning or its activation. So let's go over with this single-layer perceptron example. Suppose that we have a set of M training examples of a set of samples X and Y, where X is the feature vector and Y is the true class label for that feature vector. And we have a set of examples such as x1, y1, x2, y2, to xm, ym. Here, x is a nx dimensional vector, and y is a label vector, that can only take 0 or 1 values. So our network will consist of nx input nodes at layer 0 and one output node at layer 1. We will see that later here. So there's a single weight vector that is formed for the connections from all nodes from layer 0 to the single node in layer 1. And there's a single b value for the bias in the activation of the node in layer 1. The output node first sums up all the inputs multiplied by the weights, where the output node sums up, let's call it z, the inputs multiplied by the weights. X is our input vector and W is our weight vector, and add the bias. Then it calculates its activation using a logistic function. That's a sigmoid. In the multi-layer perceptron, presentation, you can see different activation functions. But since our class labels are either 0 or 1, we need to squeeze our outputs in between 0 and 1. So we have here a sigmoid activation function that squeezes our outputs between 0 and 1. So this is our network. In layer 0 we have nx number of nodes, because we have nx number of inputs from our feature vectors, and we have nx weights, and we have a b value that's multiplied by 1. So our output will be the sigmoid of this summation. So our goal here is to learn the weight vector W and the bias term B using the set of training samples. For that purpose, we minimize the cost function, which can be a quadratic cost function written down like here, where we subtract our estimation from the true class label and take a square of it and add them up. However, a quadratic cost function is not a very good cost function, because it turns out the cost function, quadratic cost function, is not non-convex, which makes the gradient descent problematic. Why it's problematic? When you have a non-convex function, there will be multiple minima. So when you are using gradient descent, you can start from here, go over here, come here, but you may not climb back in order to find the global minimum, where you will be stuck here. So when we have a convex cost function, it's much better, wherever you start, like here, you always converge to the global minimum. So for multilayer perceptrons, we have the cost function that is called a cross entropy cost function that turns out to be convex for our optimization purposes. For this cost function, you multiply the true output with ln of your estimation and add that to the 1 minus true output to the 1 minus of ln 1 minus of your estimation. So here we use gradient descent to iteratively minimize the cost function in order to learn the parameters W and B. So with gradient descent, you start from a point, for example, a W. Using the gradient, you move to another point, and hopefully you will reach the global minimum that minimizes the cost function. So how do we do that? In order to do that, we repeat and for all training samples X and Y in the set of training samples, and for each W we calculate a new W such that we take the old value and subtract a parameter. This is the learning rate, and times 1 over n, that's the number of samples, and this is our gradient of our cost function with respect to the particular weight. So for B, we do the same. We use the old value and subtract from the old value the gradient of the B parameter with respect to the gradient of the cost function with respect to B parameter, and find then our new B value. So we do this procedure until our cost function is smaller than our cost is smaller than a threshold, or the minimum or the maximum number of iterations are reached. Now in the next video I will talk about how we do this. Thank you.